Welcome back, everybody. Welcome back to the channel. So today we're going to be talking about how to build our memory management system. Now, there's not really going to be any code in this video. This is more of going to be, again, one of those high-level videos that I talk about. Now, if any of you guys, like, because sometimes I see some of you guys don't watch the full video, I would highly recommend you watch this in its entirety because if you don't get any of the concepts in this video, honestly, you're going to have a really tough time trying to grasp the concepts as we're kind of building them as it goes on. So this isn't just for the virtual machine, but this will also go for our compiler because as we're building our compiler, the concepts I'm going to discuss in today's video are also going to be applied there as well. So just keep that in mind. So let's start with symbols. Symbols are going to kind of represent a entity in the actual executable. So kind of like how we have data entities in our compiler, we're going to have symbols at the low level for our virtual machine. And a symbol basically represents a piece of data that's going to represent some higher level construct. So we're going to have three types of symbols in our virtual machine. We're going to have classes, methods, and fields, and that's it. Now, we're kind of at a point where we're starting to get a little bit more low levels. This kind of shows you how much information you actually need. You actually don't need that much information to run an actual programming language. This also shows that all that fancy stuff that we were going over when we were talking about the parser, all that stuff flies out the window once you get to the low level. None of that stuff matters. It's just a higher level construct to make programming easier. So I didn't really write too much in here because I mean we're going to go over this later, but I just wanted to show you guys that each symbol is going to have a basic set of info, like what is its GUID, what address is it, what's the name, the full name, the type of the symbol, any access flag privileges, and the owner of that symbol. So classes can have owners, so can methods and fields. And then each individual symbol type will inherit what this is called the symbol class. So this basic info block here is representing the symbol class. And just like how I represent data entity in the compiler, all of these are going to be different classes that inherit the symbol class to get the basic info that all of them are going to share. It's common data that they will all have. So once we kind of set up our symbol system, we're going to start to talk about initialization. So this part might confuse some of you. It might break a couple of your brains, but bear with me. We'll see how it kind of works out. So I have this example here with some code. Now this is just a simple example where I create a class of A, B, and C. Now I'm not doing anything with the classes. I'm just showing you guys how it's actually allocated. So here's how it's going to be allocated on the memory side or on the virtual machine side when my virtual machine sees this data. It's going to create three separate classes. And as you notice, so we have like the A class, which has a value of size. We have a B class, which also inherits A, which has no fields. And then finally, we have a C class that inherits B, which inherits A, and A has the size field. Now, if you notice, all of these just have the size field. So if we instantiate all these classes, this would be the size of all of those classes in memory. Now, if you notice, the C class has a static value of name. This is going to be a bit confusing, but static fields are not the same when it comes to like instantiation. So when we access static data, we're going to be accessing on a static heap. This data is going to be allocated and put on either the stack heap or even potentially the static heap. It just depends. We'll go over that in a few minutes. But just keep that in mind. And as you can see here, I also have addresses as well. This is very important. You want to pay attention to this. So each of these classes are going to have the size address of 0. Now, let's look at a little bit more of a complex example. Now, this is another example of instance initialization, where we basically want to instantiate A, B, and C, but the difference is that we call this size or set size function, and we pass in the C class, but because the C class inherits A by virtue, because it inherits B and that inherits A, we can allow us to pass in this A or this C class into this A function, and we can set the size. Now, here's where it gets important. If you notice, all of these have, the size, but with the exception of C, C now has a next field. As you can see down here, C has a next field right below the static field, and that has an address of 1. Now, this is a perfect way for you being able to see why you can do one thing but not the other. So if we try to take a class and pass it to a function that requires a C class, We cannot access it because the address of the field of C for next is 1, and A only has a size of one field, not two fields. This is also how, in the reverse, how even though we can't do it from A to C, we can do it from C to A because because the address, what happened to the, because the address of next is 1, so when we pass in the C, it still thinks that it's the A class, so we can access this size as normal. Now, the way it's going to work on our compiler is we're basically going to set up the addresses for every single class, and whatever the addresses are for that class, we're going to get the total amount of fields for that class and have that as the base address for any fields that we create in our class that we're actually talking about. So for instance, we're inheriting the A class. A already has its addresses set up of 0. When we get to the C class, we're going to count how many fields total, including any classes that is inherited. So we're going to count how many fields does the B class have, plus how many fields do the A class have. That's going to represent our base address. So it's a total of 1, so our base address is going to be 1. So we're going to assign 1, and then we're just going to keep, so if we keep adding fields here, like another one and another one, it's going to be 2, 3, and 4, and so on. So that's kind of how it works on the compiler side. Now let's look at static initialization. As you can see, this is a little bit different. So when it comes to statically initializing A, B, and C, C is the only class that has a static field of name. So that's going to be the address of 0. Now, this is where it gets a bit strange. So I know some of you guys understand the singleton pattern. And when it comes to creating singletons, that is not the same as static initialization at the low level. Java, I've actually modeled my memory system off of the Java virtual machine, so Java kind of does some similar things. Of course, I've made it my own kind of way of how I do it, but like I said, static initialization is 100% different than singleton initialization, and we'll see that shortly. So let's look at a quick example of how I do memory pooling in the actual language. So I created another example here. You can see I have a thread local of count. Now the way thread locals work is each thread is going to have a stack. Now if you guys remember, I have what's called an internal stack and a hard stack. The hard stack is going to be the physical memory that the thread can actually have available, but the internal stack is what we care about. So all these fields are going to be resting on the internal stack, all this data here. So when we access or when we create this count field, the way we segment variables per each thread is we basically allocate that amount of data on the internal stack. So let's say we have an internal stack of 10 and you have, one thread local. Well, your stack for the user is going to be 9 because the way it works is we allocate that amount. So anytime if you create, like for instance, a thread and you have like 100 local variables or 100 thread locals, and you only have a thread internal stack of maybe 90, then that thread cannot be created because there's not enough space to fit both the data required for the thread locals as well as the data required for the user stack. I do have a minimum, and we'll see that later, but I do have a minimum size for a user stack. They can't just have like a user stack of 1. So there's that. And then we also have two other types of heaps. So we have the static heap and we have the main heap. The static heap is going to be, we're going to have a static instance of class A, B, and C, and then any other classes that we have, string, int, whatever. Like as you can see here, I have a couple examples where I have a string, an int, and yeah, so, and then there's other stuff as well. So any fields or any classes that are going to be instantiated are going to be resting in here. Now we also have what's called the main heap, and the main heap is going to be the heap inside of our garbage collector. Our garbage collector is going to be responsible for holding the actual instances of each object. Now, the way it works is when we start up our program, what we're going to do is we're going to create a bunch of instances, and these instances are going to be pointing to actual sharp objects in the virtual machine. But if we look at the example here where I have like a static singleton of C, instead of actually creating this static singleton inside of the static heap, what's going to happen is at the very start of our program, when our virtual machine is getting set up, we're going to create all of individual instances for each class. And then inside that instance, we're going to access this name field and assign that field to another object that's also going to reference the main heap. So that's kind of how it works. So just remember that the static heap is not actually a reference to any static fields in here. It's just a means of transfer of data to actually get access to those static data. So if we have any static fields or whatever, we're going to have to access the instance, and then inside that instance, we'll access whatever static data we want to manipulate. So hopefully that made sense. Hopefully I didn't confuse anyone. Like I said, the Java virtual machine kind of does something similar as well. But now let's look at how I actually, like, what's the anatomy of an object? So typically the way I do objects are I have a sharp object and it has a head, which basically the head represents, I don't know why I call it this, but that represents the numeric data of that sharp object. So as I've mentioned several times in other videos, my language defaults every type to a double. So if you have like a number, it's defaulting to a double. And the only way that I have like ints and longs and shorts and all that is I do some casting at the high level to keep that high level construct intact. But at the low level, they're all just doubles. Then I also have a node, which is going to represent a list of object containers. And we'll get to what an object container is in a little bit. But then I also have other data. So I have the info. So every sharp object is going to have info. And you can kind of think of this as the DNA of the actual object. So if you think of like each sharp object as a cell, this part is going to be the DNA. You can kind of think of this part as the mitochondria, I think it is. I'm not a scientist, so I don't remember what this stuff is called. But this is like the mitochondria. This can be like the DNA of the actual cell. And this can be just other parts of the actual cell. And then this can be the, what is it called? The flagella, where cells can attach to other cells. I don't know. This is a bad example, but you guys get the point. So we're gonna have a way to reference count our objects. So how many other objects or how many other containers specifically are referencing this sharp object? And then we're gonna have size, which just, what's the size of the object? So info is gonna contain a ton of data. It's gonna contain whether or not the object has a lock on it, a mutex lock. It's going to contain garbage collection info, like what's the generation of that actual sharp object, what class does this sharp object represent, and just a whole host of other things that are very important for the sharp object. Now, most of the info in here is mainly going to be used by our garbage collector, but there are some instances where we do need to access this data. So I do have it. And then of course we have our next. So this is the main way how I allocate memory on my programming language. If any of you guys know about how memory works in C++, you know that if you have a giant array, what it tries to do is it tries to find a contiguous array of that memory to supply you with that appropriate data. What that means is if you allocate an array of 5 elements, you're going to try to find a empty block of 5 elements in your RAM. Well, in an effort to not get a out of memory exception because I'm literally accessing gigantic straight line blocks of memory, what I do is I use what's called a linked list. So basically every time a new object gets generated by our garbage collector, I assign the last object's next value, which would originally be null because it wasn't pointing to anything. I assign the next value of the previous object to the current new object that was created, and this allows me to create an infinite amount of objects so long as that there is memory for the size of one object. And I believe the last time I checked, the size of my objects in my programming language are 32 bits. So, because of course I'm trying to support 32-bit operating systems, so it works out perfectly. And then after that, we have our object containers. Object containers are there to facilitate the transaction between transfer of objects, meaning that when you have an object and you want to assign it to a new object, you're going to set the current object that you're pointing to null, and before you set it to null, you're going to decrement the reference counter in that object and then set it to null. And then you can pick any other object that is inside of the heap and you can assign it that new value and then of course increment the reference counter because now it's referencing a new object. So that's kind of the concept of how object containers work. So let's get a little bit more of a concrete example of how they're stored in memory. So I have two main examples here. Let's see, can I zoom in a little bit? Oh, that's too close. So here's an example of how objects are stored on the thread stack and the static heap that we were talking about. So what the static heap and thread stack are they're basically just an array of objects. And each object then has a pointer to a sharp object. And again, if you assign it to a new sharp object pointer, we're going to increment the reference and decrement the reference of the old object that we were pointing to. And then the main heap is just going to have an array of pointers, which are going to be a bunch of linked lists, where we're basically just going to be linking each of these objects together. So that represents the entire heap of our garbage collector. So as we're kind of traversing through our memory, we're going to just continuously go through all of these next pointers until we get to the very end. So let's kind of put this picture to an actual example. Let's say we have a thread stack, right? And in our thread stack, we're in the main function. And we want to access the local variable called data. Well, let's say we assign that local variable of data to a string. So when we assign that to a string, originally this will be null. So we're going to pick an object from the heap. So we're going to say garbage collector, create me an object of type string. And what it's going to do is it's going to create that object, add it to the very end of the list of the last final element. And then we're going to take that object and assign it directly to number 2. And number 2 is going to represent our data field. Now this sharp object goes from 0 references to 1 references. And once we're done with that and we set data to null, that then gets set to null here. And then eventually, once the garbage collector decides it's time to collect, it's going to go through and it's going to see that this object at the very end has no references, and it will destroy that object. Also, by the way, if any of you guys are wondering, okay, so if I'm assigning objects to the very end of this list every time, and every time I want to create an object, I have to assign that object to the end of this list, do I have to for loop through the entire? No, that's not how I do it. Basically, I keep track of whatever the last allocated object is, and then I just set the next pointer of that allocated object to whatever the new one is. And then I just keep doing that, and then that's kind of how it works. So that's the fast way of how I figured out how to do it. So let's get out of here and let's go to the next picture. So let's see. All right, so yeah, so here's an example of how objects are freed. So if we have a container, and let's say this is some function nested, 100 functions deep or something, and it has an address of 147, right? That's the stack address of this object. Well, when we set it to null, we're going to be setting sharp object at whatever the value is, and of course this will reference an object in the heap of the garbage collector. We're going to set that to null, but it still has one more reference to it. And this could be a function at a higher scope. So once we kind of call back all the way to, I don't know, 50 functions or something, this is lower down on the stack list or higher up, depending on how you think about it. We basically still have that reference. So once that gets set to null as well, then it'll get freed. So that's kind of how that works. And finally, let's talk about how instructions are stored in our programming language. So when we're going to be talking about our executable file in the next episode. We're going to be talking about how to process it. I'm going to start you guys off very simple, and then we'll just kind of go from there. But basically the way it works is in my executable file, I have a bunch of bytes, right? So I have a bunch of data that, is going to represent a bunch of characters, and they're 8-byte characters. Well, because my language is a 32-bit language, 8 times 4 is 32. So in order to basically build an instruction, what I basically do is when I compile your code, I generate a bunch of 32-bit instructions. Once I'm ready to output that to the executable, I destruct or deconstruct those 32-bit instructions down to 4 bytes, which represent that entire instruction. So once the virtual machine gets it, it has to then repack these 4 bytes of data back into a single instruction and add that to the list of the function. So that's kind of how it works at a high level. Hopefully that made sense. We'll go over kind of what I use to actually do that. It's pretty simple. It's just a defined statement with a bunch of bit shifting macros that kind of handle all of this stuff. So we'll see that in a little bit. But yeah, so that's pretty much everything. This is kind of a high level look at how I allocate memory in my programming language. So hopefully this was explained well. And if not, as usual, if you guys have any questions, you can always put them in the comment section below. Also, if you guys would love to help support the channel, you can always head over to my GitHub repository at androidfcd/sharp. And when you do, definitely watch, star, and fork this repository. That gives this repository a lot more visibility and let other developers know this language exists. Also, if you're curious about what I do on kind of a daily basis, you can head over to the remastered branch. In there, I write some pretty decent commits, so you can kind of get a gist of what I've been up to without really having to look too much in the code. Or if some of you are even curious about some of the stuff that I'm looking to add in the future, or stuff that I've done in the past, you can head over to the docs folder. And in there, there's 2 main files. There's a changeless file, which contains all of the things that I've done in the past to the language, as well as stuff that I'm looking to add in the future. And this was also recently updated to hold stuff about my Sharp Native Bridge. So that's going to be it for today, guys. As usual, if you're new to the channel, definitely consider subscribing, and until next time, see you guys later.